Laplacian of Gaussians can actually find the objects, outline the edge of the objects, very clean, right? Because it gets rid of the noise first using the Gaussians, and then you find the second derivative, you find the second derivative. Here's the example of applying the Laplacian of Gaussians. This is the original image. A is the original image. B is the, Sobel, right? Sobel gradient. C is the spatial. This is the Gaussian filter. And D is the Laplacian mass. If you use log filter, this is what you're gonna get. You can notice that you notice the Sobel and the log filter. It's a little bit different. The Sobel is the first derivative, right? The Sobel is the first derivative. If you notice, notice the difference between Sobel and the log filter. For Sobel is first derivative, log filter is the second derivative, right? Actually, we have learned that the log filter, the Sobel is the first derivative. You will find the thick edge, For the log derivative, for the log or Laplacian, you will find it highlighted too, You'll see the edge of the black and then white and then black, white and black, right? This is the log filter. And this is after segmentation, and this is after the zero crossing. After zero, which one? G, A, B, C, D, F. G is after zero crossing. This is G after zero crossing. So, you can apply first derivative or second derivative for segmentation as well. A lot of times, this one is good, right? It's connected, and then you do the zero crossing. However, many times the edge points are disconnected, due to some noise, A lot of times we need to link the edge together, To link the edge together, we form a boundary, A boundary means they are connected edge, We can apply the boundary, the edge linking, into different ways, The local processing and the global processing. For the global processing, we're gonna learn half transform. The other way we do is graph theory. Let's do edge linking. Edge linking using local processing. We link the edge through two things. The magnitude and the angle. If the edge has similar magnitude, that means you got to have the reference edge point, which is x0, y0. Gradient of f at x0, y0, which is the reference edge point, and then you consider the surrounding edge point near x0, y0. If the surrounding edge point are similar, similar means what? The difference is less than a certain threshold. Like I said, if they cannot be exactly the same, right? So if you want to find they are the same or not, you cannot do that. You cannot say delta f x y equal to delta f x naught y naught. It's impossible in programming. So you have to find the difference, and it got to be less than a certain threshold. And the other thing you can do is the angle. Remember, the angle we defined previously, the gradient in x, gradient in y, right? And the magnitude, and then the angle will be arctangent. Okay, the arctangent of gradient in y over gradient in x. Okay, so this alpha is the arctangent of gradient in y over gradient in x. Okay, so basically you have two images, right? The magnitude of the gradient and the angle of the gradient. Okay, and then again you compare the angle if they have the same angle or similar angles. Okay, then you decide. So if the difference is less than another threshold, then you can see that these 2 points are supposed to be connected. That means any pixel in between got to be turned on, okay, as edge. Okay, and that's how you link the edge. Okay, here's the example, okay, for edge linking locally. This is the original image. Okay, this is the gradient or vertical gradients, right? You can see most of the vertical line will appear. Most of the vertical line appear. This is the horizontal gradients. Okay, if you combine the two, okay, without the angles, okay, you are not going to be this clean. Okay, like this one, the horizontal line here, you can see there is no relationship between the angles of them. Okay, if you use the angle information, this edge would not appear. Okay, you cannot just have magnitude and phase and then horizontal gradient in x plus gradient in y. If you have gradient in x plus gradient in y, you'll see all these lines as well, right? Over here, if you use the local edge linking, this is what you're going to see. You'll be a cleaner ones, particularly at the license plate. You can see here the license plate, due to the different angles, it would not appear. Okay, it only appears as the horizontal line and the vertical line. Okay, and that's how we do edge linking. Next is edge linking using half transform. Okay, edge point that are linked using the half transform is basically global. Okay, it's global processing. This is what we do. Edge point are linked if they lie in the curve of a specific shape. Okay, you could use that local processing. But however, in the way to detect the straight line, suppose if we have points that are candidate for a straight line, okay, that are candidate for a straight line, okay. One of the way we can do is that we check the gradients, right? We check the slope of each one of them, each 8 points. If you check that, if they have the same slope or similar slope, then you connect the dots, okay? To do that, suppose you got n edge point, and if you want to connect all these edge points, what you have to do? You have to do n choose 2, right? So you got to pick. Suppose you got n candidates, you pick these two points, and do they have the same slope? You pick these 2 points, do they have the same slope? You pick these 2 points, do they have the same slope, and so on, right? So in this case, you use n choose 2. N choose 2 is approximately n squared, right? It's n times n minus 1, the whole thing divided by 2. So it's approximately n squared, okay? To find the subset, okay, then we have to find all the subset of points that are close to a particular line. In this case, you got to find multiply by n. So this process is done with n cube iteration. Imagine n cube iteration. Suppose you got 100 edge points and you have to do this one to find the straight line. How many you have to do? How much is 100 edge point cube? 100, พัน หมื่น แสน ล้าน 1 million iterations. Okay, it can be very tedious. Okay, so half come up with a more efficient way to detect a straight line. Instead of using a million, okay, of iterations, okay. Huff in 1962 came up with a more efficient way to define a straight line. This is Huff is doing, okay. Huff says there are two parameters for the straight line, right? For example, y equal to ax plus b. This is an equation for the straight line. Okay, this is an equation for the straight line. Every single xi and yi on the same straight line got to have the same value of a and b. Right? Got to have the same value of a and b. Have to think backward. He says, I can change these equations into b equal to negative xi and a plus times a and then plus yi. This is also an equation for a straight line, but horizontal axis is a, vertical axis is b. Okay. This one here on the left, horizontal axis is x, vertical axis is y. Okay, you got a straight line with the same a and b. So over here, if you change the axis, okay, to a and b, you can see that every single xy that goes in, okay, you can get, for every point xy go in, you're gonna get one straight line, okay? And all these straight lines supposed to intersect at the same point A and B. Can you see that? Okay. So one point here on the left becomes one straight line on the right. So every single point on the straight line here becomes the straight line that intersect at one point A and B. And Huff says, from this space, this is called the parameter space. From this parameter space, I can find the longest line. Okay, the line with the most A and B, same A and B, is the longest line in the image. You see that? Okay. So this is how the Huff is doing. So Huff says, and then you implement in the digital world, right? So you define B min, B max, and A min, A max. And then for each particular point, x, y, xi, yi, xk, yk, you put into this equation and then you plot these graphs, okay? We call it the accumulator cell, and then you see after these cells, at the end, you pick the one with the most values, okay? That will be the corresponding line, okay? This method has been used a lot because you can use it in computer, and it doesn't take n to the cube iteration. It takes only n point, okay? Because if you got n equation, n h point, you just need to do iteration n times, right? So it's a lot faster, okay? It's a lot faster. You use iteration only n times, okay? And then you will detect the age. However, this original Huff method there is a flaw, okay? There is a flaw on this original Huff method. Why is that? If you notice, where is the flaw of this method? If you change from this straight line to this straight line, we notice that what is A in terms of this straight line? It's the slope of the object, of the line. B is the y-intercept. Y-intercept is usually no problem, but the problem is with the A. What happens if A is vertical or almost vertical? What is the slope of the vertical line? What's the slope of the vertical line? It's infinity. That means if you got a straight line that is almost vertical, when you put it in here, in the accumulator cell, you need A from negative infinity to positive infinity, which is almost impossible. Okay, so you cannot really detect the vertical line. Okay. So somebody else came up with a modified half method. Okay. The modified half method says the problem with y equal to ax plus b is when a goes to infinity or the vertical line. Somebody came up with another method to define the straight line. This is another way to define a straight line. X cosine theta plus y sine theta equal to rho. This is basically the polar form of a straight line. Okay, the polar form of a straight line. The theta, the rho measure from 0, 0, okay, from 0, 0 to the radius that is perpendicular to the straight line. Okay, the radius that's perpendicular to the straight line. And theta is the angle of that radius with respect to x. Okay, this is the angle theta and the radius, rho. You can see here, if you change this into the parameter space, the theta and the rho, what's the smallest value of theta? What's the smallest value of theta? 0. What's the maximum value of theta? 180 degree, right? To be horizontal line 0, and then it goes to 100, and then it comes back to 180 degree, right? So the theta is valid from 0 to 180 degree. What's the rho? The rho is the distance from the 0, 0 to, it seems like rho could be infinity, right? But usually, if you have a limited image with straight line in it, rho is the maximum distance that it can go, right? So it's maximum horizontal, diagonal axis, right? So rho is not infinite, okay? So when you do this, there is no limitation of theta and rho. However, this straight line here, every point in this straight line here appear here in terms of sine and cosine, right? If it appear as sine and cosine, that means you're gonna end up with curve, okay? The sine curve and cosine curve like this, okay? This is, you see, the half transform, it was in 1962. So at the time, the computer program is still black and white. Okay, and this is how they define 1, 2, 3, 4, 5. Okay, the one here is when the rho is 0 and theta is 0 because it's at the origin. Right, rho 0, theta 0. You end up with this. Right. Actually, rho is 0, theta is everywhere from 0 to 2 pi, or 2 pi over to 0 to pi, or in this case they use negative pi to pi. Okay, so this is a straight line that represents this 0, 0 point. 2 here at this point, it represented by what? Rho. Right, rho is this unit, right? So you put this 2 here, and then this is, you get the curve. This is the curve for this point 2, sine and cosine, right? So you just put this value, this value, this value, this value here. You got different line, okay? You use different line. Okay. How do you take the line? For example, if you want to detect this line, for example here, what is this point? This value of rho and this value of theta give us, it's the intersection between point 1, point 3, 0.5, right? So it's this straight line, 315, represent this straight line for this point. You can see? Okay? Or if you read this one comes from what? Curve number 4, curve number 3, and curve number 2. So it's 4, 3, 2 here. Okay? 4, 3 through here, it's correspond to this rho and theta. Okay? If you want to connect 1 and 4, so you find the intersection between 1 and 4. So it could be 0, rho is zeros, okay? And theta could be negative pi or positive pi. Okay. You want to connect here 2 and 5, so this is a 2, this is a 5. Okay, so it's right here. Okay, so this is how we define the half transform. Unfortunately, we don't have this image. Anyway, so this is how you do the half transform. Go ahead and do this. We read the cameraman and we find the edge point first using Sobel. Okay, find the edge point using Sobel. We use the half transform. The half transform, you put in the edge point, the edge point. Okay, the half transform will give you 3 different values: the h, the theta, and the rho. Okay, and then you plot them, and then you choose half peak. Half peak means you choose the peak, 3 peak. That means you're looking for 3 longest line. Okay, go ahead and do that.